Good afternoon, everyone. I'm Brian Patterson, Chairman and co-founder of the eMERGE Alliance. My presentation this afternoon is about the changing face of power. I'll be talking about some critical characteristics of holonic, multi-tier, bi-directional microgrid architectures. And again, like yesterday, due to the virtual format of my talk, no refreshments will be served, although I will endeavor to satisfy your thirst for knowledge and information. So let's get going. For those of you who weren't at my session yesterday on mesh network microgrids, let me give you a quick overview. And for those of you who were, this will be a short reminder of its content. The reality is that electricity is becoming more and more critical to the sustainability of our civilization in its current form. A few days without electricity can be a very disconcerting and even threatening experience. But a week, a month, or a year without electricity, it's hard to imagine the potential impact. Given all this, resiliency becomes just as important as environmental impact. They both can have long-term detrimental impacts on society. So we must take seriously the need to reduce vulnerability and maintain service to critical infrastructure. We need to prepare for large-scale events, and we need to share responsibility for community resiliency. It's a tough and demanding list, but remember the 5 R's at the top of this chart. You'll see them woven into the fabric of my presentation. But as we push the key emerging technologies that are converging on the power industry, the resiliency goal set seems less daunting, particularly if we consider greater networking of smaller distributed energy resources and microgrid systems to accelerate their achievement, lower their cost, and multiply their ability to create value. Microgrids are squarely at the intersection of these technologies. Decentralized power systems can now take on a more distributed, but still large-scale role in providing electricity while reducing physical and systemic vulnerability, at least according to the President's National Infrastructure Advisory Council. They have an intrinsic ability to improve overall grid resilience. But what is it about microgrids that make them a better choice? Well, first of all, they spread out the objects of potential failure from damage in the system. Their physical isolation eliminates the potential for cascading impact on the rest of the system. The networking effect creates a better asset utilization and group solutions. Their holonic architecture, that is, that they can easily operate on their own or as part of a cooperative system, make them more valuable. They can operationally island the power system form of social distancing. Or maybe just think of them as putting all these virtuals together and helping eliminate the Christmas tree light string failure effect. Yesterday, I tried to make a case for transformation of the traditional electrical system to move away from a central station configuration to a distributed generation one. Look over the diagram at the left. Find where we are right now and ask yourself, which future is most likely? Centralized, distributed, or hybrid? And as a second thought, based on your view, will the system stay AC, move to DC, or become a hybrid? And think 20 or 30 years out. Probably the best embodiment of what we see is demonstrated in a relatively new platform offering from a company called Emera Technologies. Emera is a subsidiary of Emera Inc., a utility with $34 billion in assets and operations in Canada, the US, and the Caribbean. It's a multi-tiered grid network platform that extensively utilizes direct current and a semi-autonomous distributed intelligent approach to control. There's a lot more to it, and you can ask them for details, but this is an early implementation of, in my opinion, a grid of grids, perhaps the beginning of an ENERNET, or energy network. Emera is not the only one, to recognize the advantages of this grid-of-gridded concept. Others are moving in the same direction, which leads me to make the following observations. There are three fundamental characteristics that are common to all of the grid-of-grid efforts that I've seen. They utilize some form of mesh or hybrid networking of microgrids. They employ the DC form of electricity, mostly to simplify the coupling of dissimilar sources of electricity, including its storage. And they move away from hierarchical control schemes to distributed semi-autonomous ones. A broadly accepted definition of the microgrid comes from the US Department of Energy. It contains four elements of microgrid as their main components. Two of them, the fact that they have defined electrical boundaries and that they are single controllable entities, are key to their being connected into new, more resilient network topologies. These primal characteristics immediately allow consideration of a wide range of physical and management topologies, including hybrid ones. The more paths available, the more inherent redundancy and the higher the potential for reconfigurability. If you envision each of the nodes in these diagrams as nanogrids or microgrids, it becomes easy to see which topologies are preferred. But microgrids can be very different from one another. So how can they be easily interconnected in a power flow way? Well, that relies on a few critical things being taken into consideration at their interfaces, mostly form factor and physical characteristics of the power flow itself. And this is what is driving system connectivity towards direct current, or DC. Why? Simply put, DC is simple. Voltage doesn't alternate, and it is a single mode without phases. And I'll get into more detail in the next few slides here. Even for the non-electrician or electrical engineer, the difference is pretty obvious. DC on the left, AC on the right. But why then was our 100-year-old electrical system built on AC technology? Well, since high voltages are more efficient for sending electricity over great distances, AC electricity had an advantage over DC. That's because the power stations could convert their outputs to high voltage and easily transmit them, and then again reduce them to safer voltages when they got to the point of use at homes or factories. Changing voltages is done in the system by the use of a transformer. The conversion voltages are directly related to the number of coil windings of the input and output of these connections, as shown in the diagram on the left. In an AC motor, you send power to the outer coils that make up the stator. The coils are energized in pairs in sequence, producing a magnetic effect that rotates the outside of the motor in a revolutioning manner. AC frequency, in this case, determines the speed of the motor. The AC coil transformer and the AC fixed frequency motor, with no effective equivalent in DC 100 years ago, caused the evolution of the grid to be almost exclusively AC over these past 100 years. There was a short period between 1920 and 1950 where over 2 million DC microgrids did pop up to help power rural America in the heartland, where the grid wasn't quite economical. No voltage conversion was necessary in these cases, as the wires were very short and therefore less wasteful. But the Rural Electrification Act of 1936 slowly closed down those microgrids, as they were never networked in a true grid due to their separational distance. Rural electrification was never very economical, but the FDR administration used the extension of the grid as a works program. So the cost was buried into the national debt and not directly recovered in the rate base. With all that being said, you might ask, what changed that makes DC useful again today? The basic DC voltage converter will take the current and pass it through a switching element that turns the signal into a square wave. This turns the signal into what is actually AC. The wave then passes back through another filter, which turns it back into DC signal of an appropriate voltage necessary. The key here is the switching transistor. It is the modern replacement or equivalent, if you will, function, or provides the equivalent functionality of the transformer in AC. Solar PV cells generate electricity, DC electricity, by the way, by absorbing sunlight and using the light energy to create an electrical current. There are many photovoltaic cells in a single solar panel, and the current created by all of the cells added together is enough electricity to be useful. And that's what we see in today's modern photovoltaic panels. Rechargeable batteries, where energy is stored electrochemically, are one of the most cost-effective energy storage technologies. For large-scale energy storage, there are a number of advanced battery technologies to consider, such as supercapacitors, nickel, lithium, lead acid, flow batteries, metal-to-air batteries, and so on. All of them, however, take in and export DC power. Power electronics is the application of solid-state electronics to the control and conversion of electric power. The power range in these devices is typically from tens of watts to hundreds and now even thousands. In industry, a common application for this type of technology is the use in variable speed drives that are used to control induction motors. If you want to know what kinds of other things depend on power electronics, I'd kind of like to borrow a few lyrics from the Broadway show Hamilton, sung by the Schuyler sisters, if you're familiar with it. They say, look around, history is happening. Look around at how lucky we are to be alive right now, in a time when just about everything, and these are my words, is going electronic. A lot of what goes on in power management today, however, has to do with synchronization of AC, both in terms of frequency and phasing. Failure to synchronize AC can directly lead to damage and costly results when you try to couple things together. DC is non-synchronous and completely eliminates this problem. This allows a major reduction in electronics used to interconnect elements of a system or to connect one system to another. The use of DC and DC power electronics is helping resiliency in more ways than this. It's allowing renewables and storage devices to be more easily connected. It's allowing native isolation that prevents fault migration. Switching can be done real time. Circuits become simpler and more reliable. Monitoring is improved. Networking inverters provide better reliable AC grid support. And even wiring can be more secure at a reasonable cost using DC at its core. However, there's a warning here. Electricity can be dangerous without proper safeguards. And in general, we know that AC is a little bit more dangerous than DC at equal voltage and current. That's because when you get hit with AC, it tends to cause something called tetanus, and which is a prolonged muscle contraction, which makes it difficult to release yourself from the power source, whereas DC typically causes a single convulsion, propelling you away from the electrical source and reducing the potential injury. But in either case, AC or DC can be dangerous. So it's so being safe with electricity a little more involved than just saying be careful. Protection methods like circuit breakers and ground fault interrupters and arc fault detection devices are part of today's safety protection apparatus. Modern DC power electronics are enabling electronic versions of these devices that can be faster and more sensitive to these potential hazards and greatly reduce their hazardous potential, hazard and damage potential. And finishing off the list of growing considerations weighing heavy on the DC scale are future electricity loads, including electric vehicles, the Internet of Things, electroactive environments with augmented or enhanced reality, and the simple economic and population growth where people have the desire to use modern conveniences of these powered electronic devices. And I'll throw in one more wild card to add into the mix of DC considerations. Based on the rapidly evolving use of power electronics, I believe we will eventually move from the use of analog electricity to digital or packet electricity. This will send us into yet a whole new set of electrical system capabilities based on DC, favoring again the DC systems in the modern architectures. Well, enough about DC. Let's talk about control for a sec, or more specifically, distributed intelligent control. With distributed intelligence embedded at the local level, a nano or microgrid halon that is simultaneously a whole and a part of a grid becomes a self-reliant unit that possesses a degree of independence and intelligence to handle contingencies without instruction from higher authorities. At the same time, it is subject to control influence, a kind of enlightened self-interest from one or more of these higher authorities. From a distributed control perspective, each nano or microgrid operates as its own control agent without the direct intervention of humans or others, and have control over their own actions and internal states. They can interact with other agents via an agent communication language, and they have the ability to perceive their environment and respond to it in a timely, real-time fashion, and take the initiative in goal-directed behavior resulting from communication with a collective distribution of intelligent agents that work cooperatively in the network. Perhaps you're asking, why bother to go to distributed intelligent controls? As Duke Energy, the largest utility in the country in terms of customers served and the third largest utility user of solar PV, they provided a simple answer to what could otherwise be a very complex subject in this summary chart shown here, published in its report on distributed intelligence. They believe that the accelerated deployment of distributed generation systems such as renewable, solar, wind, microgrids, and storage, etc., are really putting a stress on centralized control. Conventional information systems used for central station control were really designed for a few large primary generation facilities and cannot adequately support new consumption modes, new generation, distribution, storage, and consumption in a dynamic environment. Microgrids by their own nature are complex systems. The proper application of intelligent control at this level is important. It's also important that they allow interconnection of a somewhat varied and reconfigurable collection of energy resources. And finally, that their control is capable to present the microgrid to the rest of the network as a single entity, agent or object in the network, both in physical and cyber terms. Turning the complexity of the microgrid into a unified whole simplifies its ask-offer transactional interaction with the rest of the network. While they internally optimize their own complex operation, including applying game theory where both the assumption of rationalization and maximization can be applied, to achieve a simplified single executable result, looking from the outside in the ask-offer environment is the objective. An object, and with object thinking, you have to think differently. There are a long list of operational advantages to this thought process, including things like better concern management, modular treatment of the elements, maintenance and debugging coincident with real-time operation, complexity reduction, we've said that a number of times, functional reassignment, and prompt collaboration, all of which can enhance the system's resiliency. The relationships between nanogrid, microgrids, and macrogrids can become usefully symbiotic. Bulk grid support can include things like frequency support, voltage support, the addition of captured energy reserve, peak demand mitigation, and basic energy production at the grid edge where it is used. So to summarize, a grid of grids will recognize and promote adding new power capacity at the edge, better accommodate natively electronic load storage and generation, enable non-synchronous operation, employ the benefits of mesh topology, rely on holonic control architecture, and fundamentally enable energy as a service valuation. Once again, that's all the time we have for today, but I'd like to conclude by saying that the eMERGE Alliance continues to work toward completing new Vanguard power standards to achieve net zero energy buildings and campuses in a highly resilient neighborhood and community microgrid environment. The rest of the portfolio standards work at eMERGE includes residential nanogrids, commercial industrial nanogrids, information communications technology nanogrids, EV charging infrastructure, indoor agricultural nanogrids, DC metering, and dual input AC-DC power supplies. The eMERGE Alliance is a nonprofit open industry association made up of commercial, government, and academic member organizations who are developing standards leading to the rapid adoption of these hybrid AC-DC microgrids. The standards facilitate greater energy resiliency and sustainability while maximizing the potential to use of distributed clean and renewable local energy. You can learn more about eMERGE at www.emergealliance.org, or for direct support, you can send us an email at help@emergealliance.org. The eMERGE Alliance participates throughout the year in SPI, ESI conferences and other events, including North America Smart Energy Week, the largest event in North America of its kind, where we have facilitated the demonstration of live microgrids that have provided power to previous face-to-face shows. In this year's virtual event, eMERGE is proud to co-host the Smart Energy Microgrid track along with the Smart Electric Power Alliance in this year's program. So thank you, and I hope that you stay connected and enjoy the rest of today's Smart Energy Microgrid presentations. And on behalf of all of us at the eMERGE Alliance, have a great day.